This is the construct. It is our loading program. Here we can load tutorials on anything. Recursion, big O notation, sorting algorithms, anything you want. Yes, we're in a program. And with what you've seen so far in this course, that shouldn't be so hard to believe. But you see, not everything is as it seems. This is what you may think your code is running like. But this is what your code may actually be running like. But don't worry, because we have a solution. Inside of this Platinum Walkman is a compact disc, which holds the secret to speed optimization. So join me, if you dare, as we embark on an adventure to take back the runtime efficiency of our code and ace this course.
Hello fellas, hopefully you can hear and see me just fine. So today we'll be going into some details on how to use that efficiency tester, which was released for assignment 2, not just for assignment 2 but for other things as well. And then in addition we're going to go into recursion and kind of the basics of that. So just wondering how everybody's doing with the assignment, with the speed tester and with all that stuff. If you can shout it out in the voice or in the chat, that would be welcome. And I'll in the meantime send the GitHub link for today's code along. Fair enough. It's alright. Well, we're not doing the assignment stuff today. We're going to be using a similar tester, though, similar to the assignment 2 speed tester. So, it'll be same procedure for installing it. So when you do get to doing the assignment 2 with the speed tester, this will be the same speed tester you'll be using in assignment 2. Alright, so starting off, I've sent the link to the code for today. And additionally, you're going to want to go onto My Courses under Content, and then under Assignment 2. And then there's going to be one called Speed Tester. You just download this file, and you should get this zip full of various code. And in there's going to be a speed tester file, which we're also going to be using today. I'll be showing you how to use that tool, which will be very useful for assignment 2, because this is what you're going to be using to determine your runtime efficiency. But I'm going to be showing it in the scope of the list of links and the stack and the queue classes that we were doing before, as well as the iterator. And then we're going to use that to kind of transition into doing some recursive algorithms as well. So let me know how you guys are doing with the cloning of the project and the downloading of this stuff. And, well, I'll, in the meantime, show you the library installation. So to install the library in your code, once you've cloned it, the procedure is relatively simple. To clone the project, again, you take the link I sent to the chat. Not found. Ooh, interesting. Let's see what's going on with that. Did I send you guys a bad link? I might have sent you guys a bad link. Yeah, it should work, because I literally have that exact link open here, but I'll share it like this as well. Interesting. Okay, well, the link that was sent by one of the people didn't work, so I'll just send the exact same link again. And maybe that will work better. Alright, so that's the repository for today. So, you guys know how to clone that. Just VCS, get from version control in IntelliJ, in Eclipse. The steps are to install IntelliJ, and then do the same thing I just did over here. Alright, so you'll get this zip file from My Courses as well. That's just downloaded from, well, I'll go back to it. Just downloaded from Content, Assignment 2, then it's the Assignment 2 speed tester file. You'll get this zip. So what you do then is in this project you'll notice it's got red. It's not going to compile. That's because there's no speed tester here. It's got a red on the imports and then a few of the lines. So what we do in order to fix this is we have the external libraries here. But we go on this blue folder with the 3 blue squares. We click on that. Under libraries, we might be somewhere else in the start, but we just click on libraries and then we click the plus, the Java, and then we drag in our file that we want. So for me that'll be Windows. If you're on a Mac, it's Mac. Then that's how it goes. So for me that would be runtime tester windows.jar, importing, and now all of this is working. So once you guys get that set, which I'll give you guys a second to do, I'll let you guys sound off in the chat once it is ready to go. I'll get to showing you how the user interface for this tool works and how we can use this user interface to really test the efficiencies of our methods. Where do we go in File? So this was to clone the project or to install the library, Tristan. Okay, so to get to project structure, there's next to where you have at the top your build icon, your add configuration, your blue arrow down for update project, all these ones, you have this little folder icon with 3 blue squares right at the top corner. You should see that where my mouse is. I can even zoom that in for you here. I'll do that really quick. Oh, I don't want to drag my window. I want to zoom my window. So you can see right here is this blue folder icon that you click. And then I'll reset that. Alright, so then you click on that, and then you can click libraries, and then the plus icon, and then Java, and then you just drag the library for your OS into there from the zip file. So for me, it's -Windows. For you guys, it might be -Unix, -macOS, depending on what you're using. And then it'll work. So then, once you guys have that installed, you just click Run on the list of links tester, just like before. And it's going to do our test methods from last tutorial. And it's going to show off the various runtime efficiencies. And we're going to get this kind of window. So once you guys have this kind of window open, let me know, and we'll continue. Alright, well, in the meantime, while you guys might be still getting it set up, I'm going to explain a few of the buttons that we see here. So over on the left, we've got the list of methods that we can test. These are just methods which have been tagged with benchmark. So if you can see over here, I've got some of these methods tagged with @benchmark. All of the methods that have this tag end up in this list. So we've got the ones here from tutorial 8, which are pop, push, get, recursive traversal, which we haven't done yet, and get faster. So these ones are all available to us to look at. And then I've got some comparison methods as well. So I've got ones that are built into Java from like the Java util library. So like the Java queue and the Java array list, all these different speed tests, which can, yes, the library requires you to have Java 13 or newer set as your JVM. If you don't have Java 13 or newer in IntelliJ, the way you change that is you go to project structure, project, and then here you've got project SDK. If you don't have a new one available, you can click edit, and then you can click download JDK plus download JDK. And that'll help you automatically download the latest version. I'm testing on Java JDK 15, but this library has been tested to work on Java JDK 13 or anything newer than 13. So yeah, that is for that. Once you have it going, we'll have this. We have the list of methods on the side. If you hover over a method in the list of methods, it'll give you a little description about it, if I bother to write a description. So, for example, the fast sorting describes it as, well, it's the speed of optimal sorting algorithms. All the little ones have some kind of description that'll help you out. Then on the graph view here, the graph is actually graphing the runtime of the method in nanoseconds versus the amount of data that's put into the graph. So if you remember the lectures on big O notation and runtime efficiency, you'll know that the amount of stuff in the data set versus the amount of time it takes to run the method is what big O notation is talking about. So it's talking about the input size versus the runtime. And here we can actually see the plot of input size at the bottom, so we're at like 300 and something items in our data set, and how long it's taking to run. And we can see that this blue one, which is O of n squared, is running really slowly. And we can see that this yellow one, O of 1, is like a line at the very bottom of the graph, which just shows you the difference in speed. If we turn off O of n squared here, by clicking on the methods, you can turn on and off any of the methods that you want. You can click reset to turn all of them off. You can click refresh to restart the graphing. So if I turn on O of n squared and O of 1, and I want to watch this play from the start, I can click refresh. And if I want to clear my selection, I can click reset. If I click help, it'll bring up a web page, which is outdated and has a few old instructions on how to do this. And if I shake the window, it's going to close everything because I'm running Windows. Terrible operating system. All right, give me a second. Okay, I want this, and I want the zoom. Alright, so hopefully you should be able to see that this is still here. Nothing is selected anymore. Can I pause it? You cannot pause it. That's not something that's a feature right now, but you could take a screenshot, or you can just watch it grow. You can increase the simulation delay. So there's 3 sliders at the bottom here. Steps per iteration, step time, and simulation delay. The simplest one is simulation delay, which you can turn all the way up, which will make it run slower. So with simulation delay turned all the way up to 1000, it should help your computer run it more easily. It'll just take 1 second for every new data point to generate. So you can see if you crank the simulation delay slider to the maximum, it's going to be a lot slower, and that's kind of effectively pausing it. So hopefully that can help. And if you don't want that, if you want it to run fast, you can crank the simulation delay all the way down, and it's going to simulate ridiculously fast. And that might also be something that is worth considering. So, yeah, simulation delay slow, simulation delay fast. That is what that slider does. If you put the simulation delay very low, the math might lose some precision. So you can see that these mathematical methods should normally be straight lines. But if we turn the simulation down really low, they might get a little jaggedy. That's not actually to do with the... Well, right now they're straight, so it's behaving itself. But sometimes they have some jaggies if you turn the simulation way down. That's just a glitch. That's not actually part of your notation. But here with the simulation delay turned all the way up, all the way to the minimum, it goes really fast. Turn all the way to maximum, it's effectively a screenshot. Hopefully that makes a bit of sense. It'll help your computer sound less like a jet engine. And if you hover over it, it'll give you a description of what that slider does. The next slider over here is called adjust step time. What adjust step time does is it lets you set the mathematical constants for the mathematical comparison methods. So if you look here, these math methods, I'll put the delay somewhere more reasonable. These math methods kind of give you a graph of an ideal. But if you compare, let's say, fast sorting n log n to an actual fast sorting algorithm, the fast sorting algorithm looks like it's above the n log n line sometimes, which is not really accurate because, big O notation is supposed to be the upper bound. So what we can do is if we adjust the step time, we can actually change, not steps per iteration, sorry. That's a different slider, I think the wrong one. If you adjust step time, you can actually change how high up the mathematical ideal curve is going to be. It's like the constant term before the multiplication. So if you imagine this math term is doing n times log n, this is like the constant that you put before n. So it's how long each step is taking. Here, comparing to this array list sort, I would say an accurate step time would be somewhere like 31 for my computer. So no, that's a bit too ambitious. So we could maybe do 107. So we can see we adjust the slider, we can put our theoretical to be just the upper bound of our real one, and that's kind of how we can compare our big O notation. So now if we set the simulation delay real low, we can see how it grows, and, well, this one is not exactly precise, but it's kind of upper bounding it, you can see. But the spikes are also not necessarily to do with the algorithm. If we adjust the simulation delay, we can make the curve line up a bit better. Yeah, you can see it kind of scales in the same way. You can really tweak it to get it perfect on the step time to really make your method line up with the ideal if you want to compare them and really prove that it's the same. So that's the step time slider. Then we have the last slider, which is steps per iteration, and steps per iteration is the most important of the sliders. What it does is it can crank the size of your data set super fast. So if you turn it up, you can see at the bottom here the numbers just went from 187 to 54,000. That's because this one changes how many things are added to the data set at each step. And this can really grill your methods. If this passes, if you don't get exceptions when you have this kind of size, your method is probably reasonably fast. As in if you don't, well, not necessarily exceptions. If it doesn't take super long to run, or if you're doing recursion, if it doesn't throw exceptions, you've probably got a solid method. Because right now we're sorting 171,000 things, huge numbers. So that's what steps per iteration does. You notice when I crank steps per iteration really high, the simulation delay is no longer under my control. That's because this was actually taking my computer so long to calculate that I no longer am able to set fast simulations. So is everybody clear on everything, or does anybody have any questions about how this system works? Okay, cool. So now let's try using this system to actually improve our code from before. So before we wrote get, pop, push, and get faster. And I'll turn down the simulation delay just so that we can see how fast it runs. So I'll also turn down my steps per iteration. Not that fast. Okay, here. That's about how we want to look at it. So we can see that our push and our pop are about O of 1, because even when we get to like 20,000 things in our data set, they are not going up really at all. And our get is quite slow. It's like O of n. And our get faster is like half of O of n. Does everybody kind of see that? How the get faster method is faster than our get method, because remember the get faster goes from both ends of the doubly linked list, whereas the get method just goes from one end. So the get faster will have half the distance to travel. Like this one is going to be O of n over 2, whereas this one's going to be O of n. So that's why get faster is faster than get. And then you can see that at the bottom there we've got pop and push, which are super fast. But how about recursive traversal? Well, let's try to write a recursive traversal algorithm, and let's try to see how fast it runs. And maybe we can compare it. Maybe we should also test our iterator. I'd say we should do our iterator first to see if we can make some improvements to how fast our iterator runs. So first things we want to do is, remember, to invoke our iterator, what do we have to do? Does anybody have an idea in the chat of what we can do to invoke our iterator method that we wrote last time? That is, in list of links, we have this class iterator. Does anybody remember how we can use this iterator? We can use a for each loop. Exactly, we just put a for loop, like a for each, the enhanced for loop, to test the iterator. And if we want to test the runtime, yeah, it's okay if you weren't there last week. We did write an iterator class inside of the list of links method, and we also wrote a stack and a queue. On the Monday last week, we did a really easy stack and queue that were not optimal at all and ran really slow. And on the Thursday, we wrote an optimal stack and queue which ran really fast. So here we can use this to test the speed of the enhanced for loop. So if we type @benchmark to annotate this as a benchmark, annotations are a more complicated thing in Java that's not in the scope of this course. If you want to test the speed of a method, you just have to put @benchmark and a name above the method you want to test. So here I'm going to call it iterator speed. Right? And then I'm going to say its category is going to be tutorial 8. I'm just doing this because I'm all OCD about which kind of grouping this is going to be in, but it's actually not important. You don't have to put the category. It's just something I like to put. So then I do public static long test iterator. The name of the method doesn't matter. What matters is that we have to have an input of long, and we have to, I already wrote this entire thing right up here, and it's not recursive traversal, it's test iterator. So that's how the method declaration would work if I didn't already pre-write it for us. But in here, this is where we want to do it, at the @benchmark pre-iterator thing. The things that matter about benchmark methods is they have to be public, so that it can be accessed by the GUI. They have to be static, so that you don't have to instantiate a list of links tester to be able to run them. They have to return a long, so they can be put on the graph, and they have to take a long as the input, so they can be put on the graph. The input is going to be the position on the x-axis of the graph, and the output is going to be the position on the y-axis. So the output here that you're returning is going to be how long it took to run, and the input is going to be how many things were in the data set. So we have some helper methods here to help us write a test. One of the helper methods we wrote last time was fill list, which takes a list of links and it fills it to a certain size. So the size will be the input. What we can do here is we can say list of links, and it's going to I think it's strings that we can fill it with. Is it? No, it's integer. Integer fills. I'm just going to double check my own API. It is strings. Okay, so we fill it with strings. Equals new list of links. Now we all remember how to instantiate a generic. We have to specify what goes inside of the list, and we have to put a name on it too. Tester. So we have to put the object type, what kind of object is stored in the list, and then the name, and then the constructor. So then we can say fill list input or comma tester that just fills the list with that amount of size of stuff, right? Or did I put those in the wrong order? I think I might have. Yeah, no, what's wrong? Okay, I mixed those two up. It's actually input list of links. So input, tester, and then the input needs to be an int. We can just cast that, it's okay. You work in long, but it rarely ever gets that high, so it's okay if we cast it. And now we can, to time our iterator, we can just say long start time, so that's the time right before we start testing, equals system.nanotime. So that's saying that when we start, like before we call the method, this is the time of the computer. Then we can say for string s in tester, and then we just don't do anything in here, we just want to iterate through, and then say long end time is equal to system.nanotime. And now we can say return end time minus start time. And do you guys kind of see how this method's going to work? It's going to fill the list up to the size that we gave it. It's going to then measure what time it was when it started before the operation. It's going to do the whole operation, and then it's going to check what time it finished at. And then it's going to return the difference, so it's going to return how long it took. Does that kind of make sense to everyone? This is the procedure you use to test your own methods. For assignment 2, I supply a tester where I pre-wrote all of these for you, but in future assignments, we might not supply a tester for all of them. You might have to write your own definition like this for some of your methods as well. So this will come up maybe in assignment 3 when you're testing the speed. You might have to write your own benchmark. So here you've got this test iterator with its input. You fill the list. You do the traversal. You see the time. Let's see how it runs. It's called test iterator for me. For you guys, it might be under recursive traversal if you wrote along. And we're just going to clear it all out, and we're just going to do test iterator. And maybe it's because I'm not doing anything in the for loop, but it seems to be increasing rather slowly. Let's just crank our steps per iteration to see. No, it is actually going pretty slow. So now we can compare it to a different algorithm. Let's compare O of n squared, O of n, O of 1, O of n log n. And let's see which one takes the longest. So test iterator looks like it's going a lot faster than O of n squared. So we could just say, let's throw out all of O of n squared. It's definitely not that slow. And let's compare it to all of these various methods. Okay, so it's a lot slower than O of n log n. So maybe it's like O of n squared, but with a really small coefficient. Let's try it. Let's take our step time to be really small. Yeah, it looks like it's faster than n squared for sure, but it's definitely slower than n log n. That's also for sure. So we can see that it's quite bad, like our test iterator. So maybe there's a better way that we can do a list traversal than our iterator, because you can see compared to our ideal list traversal, it's a lot slower. Notice our ideal list traversal is going to be in red, and yet our test iterator is in green. So that's really, really slow. I'll show you guys the code for our test iterator, and maybe you guys might have some ideas as to why it could be really, really slow. So let's look at it here. This is the iterator. Has anybody got any clue as to why this iterator might be really slow? It's to iterate, it's using the getFaster method. Remember, the getFaster method is O of n over 2. No, maybe. Oh, we'll remove the to do. That's just a comment, so it shouldn't make any difference, but we can try. Yeah, that's right. So if we rerun this without the to do, it will perhaps behave differently, perhaps the same. Let's try it. I'll make the window a bit bigger. I'll clear it all out. I'll put our list or test iterator, compare it to O of n squared and O of n. You can see our test iterator is still, it's pretty janky. It's below O of n squared, but it's still a lot slower than O of n. And if we crank our steps per iteration, we can see that it just spikes right up. So O of n squared spikes up faster, but both do still really like to spike way up. And there is actually a different reason for this, is that's if we consider the speed of our method we're using in here. Notice that here we're calling getFaster. Now if we look at getFaster and we compare it to something like O of n, and we turn our step time to be something reasonable, I said something reasonable. Okay, I'm going to guess the step time should be somewhere around 113. Okay, getFaster is actually working too fast, and I think that's not legit. What's going on here? Oh wait, no, it's working pretty legit. Okay, so getFaster, sorry about the weird math method there that wasn't really working super ideally. Anyways, so this one looks like it is indeed scaling up kind of like O of n. It's definitely not O of 1, that's for sure. But in this next step, we're calling it every time. So remember, the iterator goes through every single element of the data structure, right? And at every single data element of the data structure, we are going through this method, which is somewhere like O of n. It's like O of n over 2, because we did a lot of optimization on it. We tried to make getFaster as fast as we could last time. Remember, we only traverse half the list maximum. We make sure to check if it's near the start or near the end. If it's possible, we return the head. It's really as fast as we can get a list traversal. But it isn't necessarily ideal because we still traverse the list some of the way every time. So every time we call next, we start at index 1. Are the peaks there n over 2? The peaks there are not necessarily n over 2. The peaks are actually happening because there's other stuff running on my computer. This tester is not perfect because it actually tests the real runtime. It takes like a stopwatch and it checks how long your computer took to run it. It doesn't actually check just the method. It just takes how long your computer runs. So if I look at my computer, there's some things going on it. Like, it's not just running this tester. It's also running, it's running IntelliJ, it's running Adobe Premiere, it's running Zoom, it's running OBS, it's running a bunch of different programs at the same time. Like, you can see there's like usage in my CPU that is not indeed part of this tester. And for that reason, sometimes something else, like maybe Zoom, takes over the CPU and needs to use it, and then it goes really slow, if that makes sense to you. So the spikes you can basically ignore. Maybe in a future version of this program, I'm going to make the program ignore the spikes for you. Yeah. So that should explain the spikes. There are sometimes legitimate spikes, but here it's actually always traversing to 2/3 of the list. It's always traversing 2/3 of the way through the list, because that way we can show the difference between, we can always show the difference between get faster and get if we're traversing to the 2/3 through the list. Or, yeah, for the get faster test. Anyways. So here, we've got get faster, and that's not ideal. So can anybody think of a better way to write this iterator where we don't have to traverse the list every time? And it's actually going to save us some memory, too. All right, well, one of the hints I'll give you is that we don't need a counter if we're going to do it this way. Could you note where we are? Or iterate recursively through the nodes. Right now we are noting where we are. So right now what our algorithm is, we keep track of a counter. And then every time the counter increases, we just get the node from the counter. So we go through the list towards the counter. If we imagine that, let's say that this BlackBerry represents the start of our list, and this iPhone 12 represents the end of our list. So if we go through, for index 1, it's just going to return the head, right? And then for index 2, it's going to start at the head, go 1, right? And then for index 3, it's going to start at the head, go 1, go 2. For index 3, it's going to go start at the head, go 1, go 2, go 3. Then it's going to go 1, go 2, go 3, go 4. So it's going to go like whoop, 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 whoop as the, it's going to go as the iterator goes through, if that makes sense. Like, it's going to keep traversing through and starting at the beginning. So, yeah, you can just keep the next node. In fact, yeah, it's actually very simple to do the traversal, and Jocelyn has got it. What we can do is we can store a reference to the current node we're at right now. So we can say list node E current equals head. Right, now we can say return current equals null, or current dot next equals null. So that way we can see that if the current is null or the one after the current is null, we return that it does not have these things apply. Right? So now we're telling it, instead of comparing the size to an iterator, we can compare the existence of the current and the current next instead. And now all we would have to do is we can say ecur, instead of get faster, we could say equals current dot data, and then we can say current equals current dot next, and then return cur, and then that should just about do it, right? Let's see if this runs any faster. So I'm gonna turn on our comparison for our test iterator, and we can watch how it runs. So let's just look at it, remember kind of what the graph looks like. Maybe I'll even take a screenshot of the graph, and we can compare. So here right now our get faster kind of looks like this curve going up. It's going up a lot. We're at how many iterations are we in? We're at steps per iteration of, like, let's just crank it all the way so we have a benchmark. We're currently at a maximum steps per iteration, and the second node is taking forever to run. It's basically like not even running. It's like so slow when we turn up the steps per iteration all the way. It took 65, is that 65 million? 65 million? No, it's not millions. It's, I don't even know. It's a huge number. It's like a massive, incomprehensibly large number of nanoseconds to run this iterator at size 10,000. That's pretty pathetic. So now, with this rewritten iterator, 65 million. Yeah, it took 65 million nanoseconds to run it, probably. And now, if we compare it to what this rewritten version is, and we just test iterator, and we crank our steps per iteration all the way up, we can already see it's a lot faster. We're at dataset size 30,000 and we've not even reached 1 million. We're currently just under 3 million and we're at a dataset size of 200,000. So we can see the speed increase of what we just did wasn't like a small increase. This speed increase is the difference between running this in 65 million nanoseconds to running the same size in under 2,000. At 65 million nanoseconds, we could probably sort a dataset of size 65 million versus 5,000. Like, that is the level of speed increase we just did by making those slight changes. So hopefully you guys can now see kind of the reason why we care about runtime efficiency. It's not really even about how fast it runs. It's about, can it even run? Like, if we implemented the iterator from before, the iterator that we made last time, and we actually put this into, let's say, a database program or something. Well, that database program would not work. It would simply just take too long to run, and by the time you get any operations done, it would be like 5 years later, and the operation you needed would no longer be relevant. But if you implement a fast version, you can see that the increase is very controlled. It's very reasonable. If we compare it to something like sorting an array, it should be a decent bit faster now. Whereas before, it was slower than sorting an array. And for what reason on earth would sorting something, manipulating it into the right order, take you less time than just reading it? Like, that doesn't make any sense, just logically, right? Like how could you sort something faster than you could read it? It's impossible. Now it makes a little bit more sense. Of course, these are not directly comparable because, well, they really shouldn't be. This is sorting a completely different array list with different data types built in, so much different stuff. But it still gives you an idea of the kind of rule of thumb of it, right? So that's that for runtime efficiency. If you guys have any questions, feel free to ask. Now is the time. And then I'm going to get into recursion, which is a pretty complicated subject for a lot of people. So I'd like to spend a bit of time on it. But for now, any questions about the tool that I was using, how to install it, how to use it, any of the concepts, now is the time to ask. Mike Tester says I could check out McGill Robotics. Where do I go do that? You can Google McGill Robotics. It's worth checking out. Good design teams there. Recommend joining them. The little Easter eggs in the runtime tester. Finally, people are taking notice. All right. So, besides the Easter eggs there, what else is there I could show? Well, I saw chicken. Yeah. That one was pretty tough. Shout out to people who get that one. So, yeah, we've got that. Seems hopefully people can understand it. Seems hopefully, yeah, people can understand that stuff reasonably well. In that case, I'm going to go into recursion a little bit. So the first things that I'm going to do for recursion is the easiest. So before I do, though, does anybody want to hop on the mic and try to give their best explanation of recursion to the rest of us? I don't know, I find it to be a pretty fun thing to explain sometimes. By all means, go ahead. Yeah, that's a really good explanation. That's really solid. That's basically the whole concept. In a more theoretical level, it's kind of like, imagine that you have an algorithm that works for a certain specific task that you have to repeat. So for example, let's say that you want to calculate, you want to keep dividing something by 2, right? So why would you write, divide by 2, like 4 whatever, divide by 2 until you can divide by 2 no longer? When instead you could just put, let's say an if statement. You could say if it's not divisible by 2, like if it's just 1, or if it's whatever, if it's the base case, you return. And if it's not, you can divide by 2 and pass that as an input. Imagine recursion as kind of like, in the movie Inception when they keep going deeper and deeper into the levels of the dream, and they can still bring stuff with them into the deeper levels of the dream. So they can still have the same information in their head, and they can still make changes. They can still make changes in their the dream world as they keep going deeper and deeper into the levels of their dream in Inception, right? It's kind of the same with recursion in programming, where when you go into a recursion. You bring with you all, like, some of the information. You can pass information into the deeper and deeper levels of the recursion until eventually you get to the base case. If you take the Inception movie analogy all the way, imagine they are taking the information they get from each level of dreams until they get to the situation where they're able to use that information to, whatever, change somebody's memories, and then they do that. It's kind of the exact same concept for computer science. You start the recursion with the base case, so you bring the person into the dream. Then through every level of recursion, you make progress towards your goal until at the last level of recursion, you do what you intended to do. So for Inception, you change the guy's memories or whatever, right? You do what you intended to do at the end of the recursion, and then you break the recursion. In the Inception movie, they play that like blah sound or whatever, and that kind of brings them out of it. In computer science, you type the word return, same effect. You do the blah sound or whatever, and then every level, it just goes back through. So you return from the lowest level, that has a ripple effect of returning from the level above, return, all the way up through a huge number of recursions potentially, and you get right back to where you popped up from the start. You wake up from the thing, and then you have done the changes you need to do. Then hopefully you guys have seen that movie. Otherwise, that makes no sense at all, but you should totally watch it. Anyways. That's the analogy I like to give for people who are movie nerds. If you're not a movie nerd, then sorry about the waste of time. Now, I'm going to write a really simple recursive method, the simplest one I could think of, which is checking the size of a list. Like just to see, this one we could use to make sure that our add and our remove methods are updating the index. If you were to write a tester for your own code, this would be a fantastic way to test that you didn't forget to do size plus plus or size minus minus in one of your add or remove methods. So can anybody maybe think of how we could do a recursive size check on this linked list? Yeah, that's a great way to do it. I would say we don't want to modify our list, so instead of removing it, we can just traverse it. But yeah, you're on the right track. So what we could do is we could say, let's say int count equals 0, right? Because we want to start the count. And then we can make a helper method. The reason I want to make a helper method is I need it to have an input, right? So I can say private int recursive size check int input. And here, I'm going to write some trickery, and then I'm going to explain. I'm going to say if, or no, we also want to have a node being passed to it. So we can say list node e tested. Now we can say if tested equals null or tested dot next equals null, we return input. Right? So we're saying if there's nothing else in the list, we return the input. Does that make sense to everybody? Like if we reach the end of the list, we return the input. That good? All right, so here's where the recursive step comes in. What we do is we do recursive size check, or we do return recursive size check, and then we put input plus 1, and then tested dot next. Now, can anybody kind of imagine how this is going to run? Right? If I put return recursive size check at count, comma, head. Right? Can anybody imagine how this code is going to run? I'll show you guys with the debugger when it does, or how it actually runs. But before I do, can anybody make a prediction what it's going to do? Yeah, exactly. So this is a way to, and we can actually shorten this even more. What we can do is we can remove this int count equals 0, and we can start at 0. This is just to show you guys where recursion might be useful. I wrote a really small amount of code here. I wrote 3 lines excluding the method headers, and these 3 lines are going to be able to calculate the length of our linked list. So if I add this to our test suite, where's our list of links tester? If I'm going to say, I'm going to create a new method that's going to be called test recursion. So it's going to be called public or private static void test recursions. Right, and here I'm going to say fill list, or I'm going to create a list first. I'm going to say list of links string list equals new list of links, just as usual. Now I'm going to say fill list, let's just say 15 things in our list. Oops, I did it backwards. Comma list, right? Fill our list, and then I'm going to say system dot out dot println list dot size, and then I'm going to also compare it to plus list dot recursive size check. Right, now let's see if our size lines up with our recursive size check. We'll go to list of links tester. We'll add this to the top of our method. Test recursions. And let's run it. So now the thing at the very top says 1514. Okay, so we do have an issue with our list traversal. Let's see what it is. It looks like our recursive traversal is only going up to 14, whereas our size is reading 15. Let's take a look and see exactly what it may be doing wrong. It starts at 0 and it starts at the head. Well, the problem is that it's starting at 0 and our head is a node. So it's not counting our head. So we just got to say it starts at 1. Because the minimum size, well, now we can say like if is empty, return 0. So that was one issue we had to debug really quick by testing it. It's just that forgot to check if the list was empty. Now, if we run this, it should return us the correct size. Yep, 1515. Okay, so it looks like our method works. Now let's examine what it does with the debugger. First thing it does is it checks if indeed our method is empty. It's not. Speaking of which, guys, a little helpful thing for the debugger is you don't actually have to put breakpoints over every method you're using. These are going to be really helpful for you with recursion. It's going to be called step over and step into. Have you guys seen step over and step into before? Maybe if you use Thani in Comp 206, you remember step over and step into from their debugger. Same concept. Here, we just click step over to get to the next line. And if we want to see what this method does, we click step into. It's going to step into the method. It's going to say the next is not null, so it's going to return this method again. We step into it again. And now we're at a second level of recursion. Notice that the input counter is at how many levels of recursion we're in. So now we're at the second level of recursion. We're testing it. Third level of recursion. Testing it. Fourth level of recursion. We're testing it. Fifth level of recursion. Sixth one. Seventh one. Eighth one. And now look how many levels of recursion we are down. We can actually see here in our frames our levels of recursion. This is a really cool thing about IntelliJ. It actually shows you how many levels of recursion we are down. Here, look. I'm going to quickly peek. You know how in Inception they cut between the different levels of dreams? Here I'm cutting between the different levels of recursion. This is where we are right now. So at the present time, yes, we are currently in recursion level 1. But then inside of that recursion, we're inceptioning and we're recursioning again into level 2. And then here we're recursioning again into level 3 and 4 and 5. And unlike Leonardo DiCaprio, who was, didn't have the courage to recurse more than like 4 or 5 times in that movie, we can recurse like 15 times, no problem. Why don't you check if both tested and tested.next is null? Why not just tested.next? I checked the null on just tested in case it's an empty list. Like I just made it null safe. In case this was written by a different programmer, let's say if instead of this, a list of size 0 had a head of null. What it would do is it would return, it'll have take null and 1. This actually doesn't work for this anymore because I added a second check up here. If I wanted to minimize the number of lines of code, what I could do is I could pass 0 and null with a list of size 0, and then it would here go into if tested is null, which will be true, it'll return 0. And then a null head would return 0. And that way I don't have to write as much code, but here I did an isEmpty check as well, just as a quick fix. Does that hopefully make sense? You could also, for this right now, you could remove the if tested equals null. It's just there in case you wanted to do it slightly differently. Like if you wanted to adapt how the algorithm works to take up less lines of code, you could do it like that too. Alright, so yeah, we've got all these different levels of recursion going through, recursing again, and now you can see up here in our frames, the levels of recursion are stacking up. And now, once we reach level 15, the next is null, and 15, 15. And that's how we got our thing from recursion. Hopefully that sheds a bit of light on how the recursive algorithm works for you guys. We're basically just going through many levels of this recursion. Right? And now, we can also do this to find the index of a node. And that's a really simple recursive technique as well. So does anybody have any idea how we can adapt this technique to get us the index of a particular node? And this is actually one of the best methods to get the index of a node. Does anybody have any clue? Keep a counter while going next. Recurse until you find the node. Josh Lynn has got it again. It is in fact recursing until you find the node. Somebody suggested the counter. The counter is a good suggestion, and it is also necessary. So you guys are both correct. So I'm going to try to say it. Shirshajit. Hopefully I didn't terribly butcher your name. Sorry if I did. Shirshajit and Josh have got it and know what they're doing. So yes, what we do is we keep a counter and we recurse through, but instead of checking if it's null, we check if the data is what we need. So I'm just going to copy paste this helper method right away, and I'm going to call it index of. And then here for our public index of, I'm going to say, well, first, actually I don't need to do any of that. I'm going to say return recursive size check, and the input is going to be, or not recursive size check, it's going to be return index of. And now the input instead is going to be, oh, I have to set up my counter, so. Int counter 0. Now I'm going to say index of counter head. Right? And now what it's going to do instead of that is going to recurse through, and it's going to go if tested is null and tested is next, return input. No, instead we want if tested dot data dot equals, and then we put our data. Oh, we also have to pass which data we want, right? So we can say data, and now we can say data. So now if these line up, no, it's data. If it equals data, we return the input, and if it doesn't equal the data, we have to return index of and then we put in our input +1 tested data. Now this is handling everything except for what if we don't have this data in the list? How do you guys think we could handle if this data doesn't exist in our list? Okay, so I'm thinking about the case. If tested.next is null, return -1. Yeah, Josh, you've got it. I would say return -1 is valid. I would also say that another valid solution could potentially be to throw an exception. So if we look at how Java does it in their index of methods, let's take a look at ArrayList. I'm just gonna create an ArrayList to show you like the code of it. Let's say ArrayList a equals null. This isn't actually a line in my code. I just want to have a way to get into the ArrayList code. So I'll go to declaration or usages. Here I'll find index of. Yep, indeed, you are correct with the -1. They don't throw an exception. You seem to have memorized that better than I have. Nice job. So yeah, you could return -1. You could also return an exception if you wanted to. So I would have put something like, you know, well, the legal argument exception wouldn't necessarily be correct. Depending on the program, you could write your own exception type. I think in Comp 250, what they would make you do is they would probably make you define an exception. Now, like last year when we did it, they made us throw our own exceptions for similar situations, which is something you may also want to do. So if you want to be following the Java convention, you could return -1. If you want to do an exception as well, you could say throw new, and then here I could say, for now, illegal argument exception, but you can put whatever you want. Or you could say that. So our condition will be if tested.next is null, return -1, and then here we can say, or you can throw an exception, or return null, or whatever, right? So that should work just fine. Now let's try index of. I'll add this to our little tester for our recursion. So our test recursions, now we can say string s equals list.get. Let's just call it index 7, right? And now we want to say system.out.println s. Now let's just say system.out.println list.index of s. And let's see if it gets that right. Ooh, no, it didn't. Let's figure out what's wrong. All right, so we've got a Stack Overflow. We're not breaking out of our loop. So let's figure out why. Oh, that's because we forgot to put tested.next. Don't even need to put the breakpoints. Just a silly error there. So this is what a Stack Overflow exception does. What a Stack Overflow exception means is that there is no situation where your code can break out of the recursion. So eventually, it's going to reach so many levels of recursion that it can no longer recurse any longer. If you recall stack and heap in Java, those are where you store your variables of various kinds. And the stack is where we store variables related to these method calls. And eventually, when you call this method recursively enough times, it's going to have called this method so many times that there's actually no more room in the stack to store all these methods calls. And that's when you get a Stack Overflow. And that's also where the name of that website comes from, because they tend to be notoriously hard to debug. But in IntelliJ, it's not so bad because you can actually see which, you can put a breakpoint and see at which line you're not breaking out of the recursion when you should be. So we're going to test it again, see that it works. So indeed, our index was 7. So our list is test. The content of that would be that. And the index of it was 7. Let's just see that the print line is what it should be. Yep. So actually, no. Our string was test 48597, and our index was 7. So yep, our recursive method did work. Now let's try what happens if we try to get something that isn't in the list. So if we do system.out.println list.index of hello world, and we rerun it, we're going to see that it goes -1, and that is the expected behavior. So that's another recursive method that's really useful. And for a final recursive method, it's going to be really similar to our recursive size check, and that's going to be toString. Does anybody have any clue how we can use recursion to write a good toString method for our linked list? Oh yeah, and another fun fact, while you might think about that, you can maybe write in the chat what you think about a recursive toString. I'm going to show you guys a little quirk of IntelliJ that will be useful if you're working with recursions. If I zoom in over here, you can see on the side, next to the lines, whenever it recurses, it's got this little circular indicator, and that just shows that that line is a recursive line. So if I go, once again, bigger, this line is recursive right here, and this line is recursive right here, and your recursive lines will be indicated by that little recursion icon. And that might be helpful for you at some point if you just read your code and you're confused about where the recursions are. That is what that icon is, and that might be useful for you to look at. Now if we scale this back to the normal, I said if we scale this back to the normal, yes, now we can think about the toString. Alright, have a base string and then append the data of each element and return the base string when done. Yep, completely correct. What we do is that I can just take my code from recursive size check. Alright, now we don't care about the index anymore, so instead I'm going to say string s is equal to whatever, but actually there's a better way to do it. We're going to say a string builder sb is equal to new string builder, because a string is, remember, is immutable, so we have to create a new string object and replace it every time if we just append the string. So instead I'm going to use a string builder, which is mutable. I'm going to say if is empty, return blank. All right, and now we're going to return recursive size check, and instead of recursive size check, I'm going to call it private string recursive. No, that's not what I'm trying to do. toString, and now I'm going to pass in what a list node e of type of name node, and I'm going to pass in a string builder sb. Right, now I'm going to fill this in. I'm going to say return recursive toString, and it's going to say head sb. Now here we can say if node is null, return, or return is if node is null, or node.next is null, return sb.toString, which just creates a string from the string builder. Now we can say return recursive toString node.next SB. And before we have to return the string builder, we have to say sb.append, which is how we add something to a string builder, and then we can say node.data.toString. And now if we want to put commas as well, we can put plus comma space. But if we want to be really fancy and we don't want to have one of those commas at the end of our list, what we can do is we can say if node.next is not null, sb.append, comma, and that way it only puts the comma if it's not the last element of the node. So if you guys were wondering how you can make a really pretty printout of one of these things and not actually have to have the issue of the comma at the end, and you don't want to have something silly like removing the comma at the end, then this is a good way to do it. It's only going to append the commas if it's not the last node. So that might be a small advantage of the recursive toString. But also, well, actually, yeah, this toString is probably longer or similarly long to a non-recursive option, but it's just an interesting demo of the recursion. So now if I print out the list, it should be able to do the recursive printout. And maybe it'll Stack Overflow. We'll see if we did the method right. No, it looks like it worked fine. And how many elements did it print out? It printed out 0 to 13. So it looks like, if node is null, node the next is null, SB toString, SB append data toString. If node is not next is null, append comma. Oh, it looks like it stopped appending things for some reason. Let's peep this out and let's see why it might not be doing the full list. If we turn on the debugger here to the recursive step. Alright, so we're going through here, we're appending the node content. Now SB contains test 152.0. Now we just go through. 1, 2, 3, 4, just keep going. 6, 7, 8, 9. We know 13 is where it stopped last time. 10, 11, 12. False, false. Append the data toString. Append the comma. Return that. Now this one. False, false. Append the data toString. Yeah, okay. And that one's next was null. So why was that one's next null? Okay, maybe we didn't actually have a list of the correct size, and maybe my fill wasn't actually very good. But it looks like all our other ones did 15, so that's really weird. That's really weird indeed. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. That's not correct. There's not 20 of them. What can I do? Head. Does it ever reach the data of head? Yes, it does read the data of head. Does it ever read the data of head.next? Yes, it does. That's weird. Oh, we can just examine the list contents compared to our. So on our list, we've got a tail of 14 and a head of that. And if we take the head's tail's previous and take its next, it does actually link to the tail correctly. I'm just going to remove the node as null and check this. Yeah, I know. Really weird data here. I don't know why it's not recursing completely properly. It's stack overflowing if I... No, null pointer exception. Oh, the data is null in one of the nodes? It looks like it might have a null somewhere in there. Anyways, one of these methods might be wrong. I think what might have happened is that I might be putting a null inside of my list, in my fill list. Yeah, I'm adding a null sometimes. That's why it doesn't work. Alright, so if I don't add a null sometimes, then it should work more properly, does it? Oh, closed it. Okay, well, regardless, near the end of the time, there might be some silly mistake I'm making here. Maybe one of you guys can spot it. Maybe somebody else can spot it, but we've reached the end of our time for today. So I'll just put a little to-do here. I'm going to say to-do. It's skipping the last thing. Oops. Not sure why. I'll figure it out. Probably some silly mistake. Alright, if you guys have any questions, I'm happy to answer them. Otherwise, that'll be it for today. This solution will be made proper for the GitHub release of the solutions branch. Probably some silly error somewhere in here. Or maybe somebody here can spot it. Regardless. Any questions before we wrap up? Alright, well yeah, hope you guys enjoyed it. Hopefully this made Recursion a little bit more simple for everyone. And yeah, enjoy your rest of your day. Hopefully, good luck on the assignment. Hopefully you do really well. And hopefully the tester comes in handy for your speed testing. Alright, see you guys later. Alright, literally like 10 seconds after I ended this thing, I realized what the problem was. I actually only appended the toString right at the after the check for this. So I checked if the node.next was null, and if it was, I skipped the adding the string. Like I skipped adding the comma and the data. If it was the last node, what I should have done is I should have had this return sb.toString near the end. Sorry guys, really easy mistake, really stupid mistake on my part. Put them in the wrong order. Should be very easy there. Just caught it 1 minute too late. Anyways, the correct solution is on the solution branch. Thank you guys for showing up.